Our first speaker, let me move this down, is Shehrzad Qureshi. He's actually a senior engineer from Berkeley Design Technology Incorporated, which is the folks that put on this seminar, okay? He's worked on a variety of computer vision signal processing technologies over the years. He's actually an author of a book himself called Embedded Image Processing on the TSMC 320 C6000. He has an MS in computer engineering from Santa Clara, BS from Davis. He's an inventor or co-inventor on 7 patents, with more pending. Early in his career, Shehrzad was the director of engineering at Restoration Robotics. Okay, his 2009 computer vision patent was the first issuance for that company. Impressive. Prior to Restoration, he was a software manager at a biotech startup called LabSite, and he's held individual contributor positions at Accuray Oncology and Medical Imaging and Applied Signal Technology, where he worked on some classified signals intelligence stuff. Interesting. Anyway, so let's give a big welcome to Shehrzad.
Good morning. Thanks a lot. So welcome to our first talk in the deep learning track. I'm sure many of you in the audience have probably heard of deep learning and DNNs. They've really taken the world of computer vision by storm in the intervening 5 years or so. And so this morning we're going to introduce what these beasts are and describe how they work. And forthcoming talks in the fundamentals track is going to build upon these basics and cover some other facets of DNNs, such as training or some other applications. So my name is Shehrzad Qureshi, and I'm with BDTI. We turned 25 this year, for those of you that don't know. We provide engineering and advisory services in various signal processing and computer vision, focusing a lot on embedded technologies. And some of the services include processor selection, algorithm development, software development, optimization, and of course, neural networks. And we've done a lot of work implementing these neural networks on a variety of compute platforms, including CPUs, GPUs, FPGAs, and DSPs. And before we dive into the nitty-gritty of deep neural networks, we just want to give a shout out here to Evan, Jeff, and John. They all contributed to this presentation via their work on a previous tutorial regarding the CAFE CNN framework. Okay, so we've got a lot to cover this morning. Briefly, in this whirlwind tour of deep neural networks, what we're going to go over is we'll introduce deep neural networks in general and the convolutional neural network in particular. We will then discuss the constituent layers, the innards of these CNNs, what types of building blocks make them up, and give them this, allow them to do the computer vision. And then we'll conclude with a description of the popular CNN topologies you find referenced in the literature. And as a guiding example throughout this talk, what we'll use to describe the vision problem we're solving is something inspired by ADAS, which is automated driving assistance. So we want to talk about how an ADAS system might recognize stop signs. Okay, so when we speak of deep learning, what are we talking about here? So really, we're talking about, it refers to a class of algorithms that has really revolutionized computer vision in the past few years. But how are they different from some of the competing traditional machine vision and computer vision techniques? Okay, fundamentally, in one sentence, deep neural networks, they learn from the data. They will learn and figure out by themselves what are the salient features in the image that will allow it to perceive what's actually going on in the scene. This is in contrast to the traditional computer vision approach where you use hand-engineered features and feed them through this thing called a classifier in order to get some answer out. And it's a little bit instructive to consider how the traditional techniques have fared. I mean, computer vision's been around for many decades and actually has found viable, robust solutions in certain controlled environments. For example, you find computer vision deployments in factory line automation all the time. If you've got a conveyor belt and you want a camera that can count the number of widgets and the type of widgets that are flowing across this conveyor belt, that's you can find traditional computer vision techniques that achieve that solve that problem. Similarly, in pharmaceuticals, if you have pill bottles and you want to make sure that the bottles have the lid on correctly and they're labeled properly, well, you have solutions for that. But the key point I want to make is that in those environments, everything is tightly controlled. The illumination is totally uniform. The specifics of the problem are completely defined. Now, but what happens is if you throw these systems any sort of curveball, if the illumination is off by a little bit, if there's any sort of occlusion, if there's any sort of clutter, if there's if there's something that it hasn't been trained for, well, then they fall apart. And the real world is complicated, and so the deep neural network technique is designed to address that. And so this morning, what we're going to focus on is one particular problem in computer vision or visual perception, and that is the image classification problem. So I've got that shown up here, and what the problem statement would be: okay, given if the computer is presented with an image, a frame, can it ascertain what's in that image? As humans, we know immediately that this picture has a horse and a person on that horse, and in the background there's a blurry car, a couple blurry cars. But it's more than that too. You might want to answer the question, hey, is this a daytime or a nighttime image? Or is this a computer-generated image, or is this natural imagery? So these are the types of classification questions that the classification system should solve. And this is a really challenging problem, right? I mean, this is not one of these line automation, machine vision type scenarios. I mean, just think about all the types of curveballs that the system could be faced here. You could be imaging the horse from different angles. It could be front, side, back. You might see the tail. You might not. There could be shadows. There could be clutter. Where does one object begin? Where does the other object end? So this is an extremely challenging problem. But it's a problem that actually we've come a long way, especially I would say in the last maybe 6 years. So that's illustrated by this chart here. And just a couple things to note about this chart. First of all, it's maybe a little bit backwards in the sense that we have 2010 on the right. And so you read it from right to left. So we have the most recent results on the left in 2015. And what the bars in this bar chart represent is the error rate. So, and this error rate is defined as the top 5 error rate. And what that means is that these classification systems, they come up with a number of guesses. And if the correct guess is within the top 5, like, for example, hey, I think that there's a horse in this picture with probability 77%. That's my top one. Well, hey, that's the right answer. So it's the top 5 error rate. So as you can see, in 2010 and 2011, pretty much the old competing techniques, which we're going to denote as shallow, and we'll explain why they're called shallow in a moment. These had pretty much capped out at a quarter of the time. A quarter of the time it was wrong. Okay, but then beginning in 2012 with the advent of this now famous AlexNet deep neural network, you see an immediate jump of 10 percentage points thereabouts. And then you can see that the error rate is continuing to decrease and decrease and decrease, which brings us to these triangles that are also in this plot. And what these triangles represent are the depth of the network. And so what you see is that by the time we get to 2015 with this ResNet network, we are sub 5% error at the cost of 152 layers. And this is an extremely impressive result because now you're within the realm of what a human can actually do. So we had this kind of demarcating boundary line, shallow versus deep. And let's talk about what that means. And to do that, we will consider the solution to a classic vision problem that's really important in ADAS. And we want to recognize the presence of stop signs in a car camera. Now, it's going to be a little bit hard to see here because the stop signs are pretty small, but this is a real example of a CNN picking out identifying the presence of stop signs in the frame. And this just goes to show, I mean, this is actually, the type of images that a ADAS system will be tasked with making sense of. So how might traditionally, in 2010 or 2008, how might we have gone about trying to solve this problem? Your pipeline might look something like this. You might do some pre-processing, probably a lot of pre-processing. You'll do some image segmentation. By that I mean separating the foreground from the background. You might do some contour extraction to kind of delineate where the object begins and where it ends to get a region of interest and ROI. We might, once we've identified an interesting ROI, we might do some various undistort operations to correct for the fact that maybe we're imaging the stop sign head on or from the side, from some oblique angle. Then we might actually do some shape reconstruction and, key here, some feature extraction. And by features, I mean edges or corners or those sorts of things. And those features would then be turned into, we would describe those features, turn them into descriptors, which are then pumped into what's called a classifier, which is a machine learning term. We'll go over what the classifier does later. But it goes into a classifier, and that classifier is learned, but only the features go in there. And that's why we call this shallow learning. So there's this big, long pipeline, and we have this shallow learning cascaded classifier down there at the end, and that would come back and say, hopefully that there's a stop sign present within this image. So I mentioned the features, and let's describe more. I said that the features could be edges or corners, but in fact, features are more elaborate than that. And this slide describes one of the real common features called histogram of oriented gradients, or HOG. This particular feature extractor and feature descriptor, maybe in the early 2000s, was first proposed to solve pedestrian detection. And it's multi-scale, and basically what's going on here is that you are computing a gradient, and then you're figuring out what is the dominant orientation of the gradient, and then you're histogramming that, and that the probability distribution of that histogram is your descriptor. And then this descriptor is fed through a classifier, which could be these things called the support vector machine, which would basically say pedestrian or no pedestrian present. First used for pedestrian detection, but eventually used for any number of tasks, such as traffic sign recognition or face detection. But here's the key problem with this approach, is that some engineer, some scientist, in this case 2 of them, had to actually handcraft these features and figure out, okay, like this is the feature that's going to describe my problem here. And so this works, but it doesn't generalize. I mean, the world that we're trying to describe is much too complex. So for example, if the pedestrian was occluded by another pedestrian, or there's too many shadows or something like that, it's too brittle. It doesn't work very well. So this is in stark contrast to deep neural networks. And what the idea is here is that we let the neural network figure out for itself, on its own, what are the salient features that characterize the object that it's trying to identify. In this case, we might expect that the deep neural network would figure out on its own that the salient features include this roughly octagonal shape, and that the stop sign is red, and that there's these letters STOP, and the presence of all these together, stop sign. And again, there's none of this I need to calculate an ROI. I need to, come up with this kind of esoteric, features that encode this stop sign. The network will figure it out on its own. So this obviously has a ton of benefits. Probably the most important being that, like I said before, and I think it's pretty self-evident that the natural world is just too vast and too varied to fully describe by hand. So we have to have end-to-end learning, starting with the input data and learning the whole problem from input to output. So, and then it turns out that we can actually use this toolkit. Once we've defined this toolkit, we can actually use it for any number of problems. For example, there's a bunch of other problems in vision aside from classification, detection, segmentation. We can apply the same technique, the same methodology to speech recognition, audio event detection, natural language processing, and control. Okay, so we've described in brief terms what are the benefits of a DNN and how it contrasts to the traditional techniques, traditional computer vision techniques. But let's dive a little bit deeper. Let's go under the hood and describe really what a deep neural network is. And the basic computational functional unit is a neuron. And neurons, these are inspired by human physiology and our understanding of how the neurons in our brain actually work. And it's actually pretty straightforward to describe mathematically. It's nothing more than a weighted sum of the inputs. In this case, you can see we've got input is x0 through xn, and we multiply that by a weight vector, w, and then we add some bias. So it's a weighted sum of the inputs, and then that output is then fed through some nonlinearity. We'll talk about that, why that nonlinearity is so critical, but that's a neuron. And W, again, we denote the weights as W. So let's talk a little bit about how we might construct, the world's simplest deep net to classify our stop signs. In this example here, we have our input down there at the bottom. Typically, we have the way these architectures are depicted in a diagram is that the input is on the bottom. So we have the input, and that flows into a bunch of these neurons, and these neurons are these yellow circles. And in this example, we have 6 neurons in our layer. And so since this is an image that's coming in, each of these 6 neurons would take the RGB values of all the pixels and weight them, add the bias, and feed it through some nonlinearity. And what we're describing really is this is called a fully connected layer. This is because each neuron is connected to each and every input value. And so then during this training process, the optimizer figures out what is the best W and what is the best bias to solve the problem at hand. I'm not going to go too much further into how this optimizer works. This is actually training, which is a whole other topic, and actually will be the next talk after this is going to cover training in more detail. Okay, so we have that really simple network, but as you might imagine, that's not a very deep network at all. In fact, real DNNs, they have many more layers. And again, by convention, when we draw these things out, we usually have the input layer on the bottom, and then it flows up, it bubbles up. And now what we've done is we've introduced 2 layers in here. So we have 2 fully connected layers. We've cascaded them. So each layer is taking the data from the previous layer and producing some set of output. And if we cascade these layers, they form a network. And a network of more than 2 layers, we call that a deep neural network. Okay, so we have this fully connected layer. But now the question is, okay, what kind of layers to stack? And as you might imagine, there's a whole number of different types of layers. But a really key point that I want to make is that in order for these networks to really work well for vision, is that you really have to intersperse some nonlinearity into the topology. And let's talk about why that's so important. So in this example, we've described mathematically a two-layer network. We have x2 being a function of x1 encoded via this w1, the weights. And then we have x3 as a function of x2. Now, these are both linear. And in fact, because they're both linear, we can actually combine W1 and W2 into W combined. And as a result, X3 can actually be described with just X1. So in fact, this two-layer network is actually nothing more than, in reality, mathematically, is nothing more than a one-layer network. We've really added no extra expressive power to this network by simply stacking two linear layers together. We have to introduce some nonlinearity in order to be able to represent something more complex. So for example, we could add a nonlinearity known as the rectified linear unit, or ReLU. This is actually pretty easy to describe. Basically, the input, if it's less than 0, gets set to 0, and if it's greater than 0, it's just left as is. So it's really critical to interleave these nonlinearities, because now if we do that, if we generate x2 through our linear expression there, and then we fit in this, if we plug this x2 ReLU of x1, if we add this ReLU guy in there, now x3 cannot be computed as a linear function of x1. And there's a bunch of other nonlinearities. We'll go over those, but hopefully this describes why it's so critical to introduce the nonlinearity. And we'll discuss in a more graphical sense how that works. So let's consider a real simple linear classification problem. Let's say we have some observations, and we have these two clusters here. We have a red cluster and we have a blue cluster. And the job of a linear classifier, would be to group these guys into two bins. We want to separate them. And armed with this matrix multiplication, we can actually do linear classification. And so a linear classifier would effectively learn the line that separates these two clusters, as so. So given an input point, x1, x2, we could project this, we could use the learned classifier coefficients to gather that would tell us what side of the line the point lies on, and we would be able to cluster the data this way. And so this works great for scenarios like this. But in practice, the real world is more complex. We need more sophisticated classifiers, and simple linearity is not going to be enough. Here's another example. So we have this cluster of observations of samples near the origin. They're one cluster, and we've got the red points on the outside. And so, armed with just linear classification, can we get a line that separates these two? I don't think we're going to be able to, right? No matter how hard we try, we're never going to be able to get a line that separates these two guys, armed with just with a linear classifier. But if we introduce some nonlinearity, such as in this case, we've got this convex hull, we can actually separate the data into two clusters. So there's a number of different types of nonlinearity. We've already introduced the rectified linear unit, but there's a bunch of other ones. But when in doubt, use ReLU. That's the one you find in just about all of the CNNs out there. Sigmoid is one to avoid. It's actually an impediment in training. And sometimes you'll hear these nonlinearities. They're referred to as activations. And the analogy is, again, to human physiology, where the neurons in our brain fire when they're excited by some stimuli. Okay, so we've discussed the fully connected layer. We've discussed the importance of nonlinearity, but we actually can gain a lot more visual perceptive power by introducing another type of layer. And let's talk a little bit about that. So for visual perception, we need the network to capture some sense of spatial coherence. So by that we mean that pixels that are close together, that are grouped closely together, are closely related. This is the idea behind receptive fields. And then in addition to the receptive fields, the ordering matters. For example, if I take my picture of this cat and he gets scrambled around, I know immediately that this jigsaw puzzle is not a cat. So the relative ordering of these receptive fields is important. And vision is really hierarchical in the extreme, right? We start off kind of describing images as really highly granular things like edges and corners and little features, and then we build up. So we increase our receptive field. From edges and little features, we get parts, and then from parts we can start to think about how do we represent objects. And the toolkit that we use, the primary tool to get some spatial coherence and receptive fields is the convolution layer. So the convolution layer is important because it gives us the spatial coherence, but it also gives us this what's called translational invariance. And it does this by doing weight sharing. And what that means is that our stop sign is a stop sign no matter where it appears in the image, right? So the convolution, and we'll kind of go over the mechanics of the convolution, but the convolution layer gives us this concept of translation invariance, which is really what we need in order to kind of tease out the spatial coherence of the image that's coming in. So currently, right now, this is the convolution layer really is our workhorse layer for visual perception, and it's currently our most successful model for visual perception. So now we'll dive in more into the mechanics of how do we actually implement all of these layers. We've been introduced to the fully connected layer. We've been introduced to some nonlinearities, and we've talked briefly about the why we need the convolutional layer. But now let's talk about, okay, in an actual network, how do we actually implement this stuff? How does it work? So I'm willing to bet a bunch of you in the audience are probably familiar with convolution in the context of image processing and 2D filtering, where you actually slide a convolutional kernel around an input frame. So with CNNs, we have 3D convolution, which really just extends the multiply accumulates out to this third dimension. And that's why we call it 3D convolution. And so one thing I just want to reiterate here is that please don't confuse the fact that it's called a 3D convolution with the fact that this example has a 3D input, has a 3-channel input. There's nothing that says that the number of channels here couldn't be 6 or 128 or 256. In fact, in real networks, you have a much wider input. Okay? So the convolution kernel is spatially local. What that means is that its spatial extent is going to be smaller, much smaller than the input it's filtering, and it's cross-channel, which means that's where the 3D part comes from. So that's shown here, where I have my input to the layer is a 3 by 32 by 32. You can envision that being a small RGB color image, and my convolution kernel, my convolution weights, are 3 by 5 by 5. And so at each convolution lag, I'm going to perform 75 multiply accumulates to generate a single output. That's shown here. So we're at a single spot in the convolution space, and we're going to perform this basically a dot product with Wx, and then for good measure we tack on this bias, which is a single scalar addition at the end, to give us our single output. But now we're actually going to slide this across the entire input. So with a stride of 1, we'll talk more about what the stride means, but with a stride of 1, if we then do this 3D convolution, our output would be 28 by 28 by 1. We're ignoring the edge effects. That's with a stride of 1. If I had a stride of 2, what that means is that I skip every other pixel location. In which case, if I had a stride of 2, the output would be a 1 by 14 by 14. But it gets even more multidimensional than that. Typically in these CNNs, you would have, I guess you could call it like a filter bank. So instead of one 3 by 5 by 5 kernel, I might have n of them. In this case, I have 6. So my filter bank, if you will, is 6 by 3 by 5 by 5. So I repeat this convolution process multiple times using different 3 by 5 by 5 convolvers. In which case, with a stride of 1, I end up with an output of 6 by 28 by 28. If I had a stride of 2, I would have 6 by 14 by 14. And these filter banks mathematically are represented as, they're called tensors, basically multidimensional arrays. That's why you hear this term tensor, in TensorFlow or in TensorRT, and a lot of all the frameworks represent these filter banks as tensors. So during training, the optimizer learns the best weights or filter coefficients and bias terms. And sometimes, again, it's instructive to visualize what these might look like. This visualization is taken from an example that's designed to recognize human faces. So again, at the lowest level of the network, we have, if you plotted the filter banks, you can see that they're kind of quasi-edgy textures, maybe look sort of like HAR filters, real low-level kind of features. And then as we go up, as we bubble ourselves up the network, as we go into the middle layers, you can see that the network is starting to tease out parts of the object, eyes, things that look vaguely like ears, mouth, that sort of thing. Until finally, when we get to the very top of the network, towards the end, the network is starting to represent objects, the whole face. So that's the convolution layer. Now we also can introduce what's called pooling layers. So remember that with the convolver, we could have a stride other than 1, which had the effect of achieving a subsampling effect, or equivalently, that's a reduction in the spatial resolution. You can achieve much the same thing with this pooling layer. This is rather straightforward to explain. If we're doing 2 by 2 pooling, for example, with a stride of 2, if we're doing max pooling, to generate the output, we're taking the max of that 2 by 2 region. If it's average, we're going to take the average value in that 2 by 2 region. If we had we can have a stride of 3, we can even have a stride of 1. So if we have a stride of 1 and we're doing average pooling, you're actually just doing a low-pass filter in the classical sense. And currently, right now, most of the time in a lot of the networks, it's 3 by 3 max pooling with a stride of 2. So pooling allows us to reduce the resolution, which is effectively increasing the receptive field. It also saves us some computation because we're going to be dealing with less elements in our feature maps, and also gives us suppresses some noise, particularly with the average pooling. That's really acting like a low-pass filter, so that's going to give us some noise suppression. And now we've already encountered our fully connected network a few times. What this slide is describing is kind of the mechanics of transitioning from a convolutional layer to a fully connected layer. Typically, the common pattern here is that you have convolution layers from the bottom up to the top, and then towards the end, you end up with some number of fully connected layers. So in this case, what I've described is the output from the convolution layer is a 2 by 2 by 2 tensor. This gets rasterized, into some input vector, unrolled, if you will, and then the fully connected part, the W, this turns into a vector matrix multiply. And then you add the bias at the end. Okay, and last but not least, we have this classifier layer. It's really a quasi-layer. Its purpose is to generate a probability measure for each of the output classes. A common one is this so-called softmax. And what it does is it'll take its input, which is usually the output of a fully connected layer, and softmax maps those values, normalizes those values, if you will, onto a range from 0 to 1. And you can interpret these as the final probability that the original input lies within a given class. So for example, we could, in our stop sign example, if we had a terminating softmax layer, it could tell us whether or not, it would give us a probability if a particular sign is a stop sign or a yield sign, you have one of these per class. And if you sum up all the probabilities of softmax, it should add up to 1. Okay, so just to review real quickly the types of layers we have. The convolution layer, that's our workhorse for visual perception. In some sense, it encodes the perception of what's present in the scene. It's kind of important to note that the convolution and fully connected layers, they have weights and biases whose coefficients are learned, are trained by the training system. And then spatial resolution, or increasing of the receptive field, is achieved by either pooling or using a stride that's not 1. And then we have our various nonlinear activations such as ReLU, ELU, and a bunch of others. And the nonlinear activations and the poolings are not trained. They might have parameters, like for example, they will have parameters, like in pooling, whether it's a 3x3 pooling or a 2x2 pooling, but they're not trained. Only the fully connected and convolution layers are trained. So now this is an example of how we describe something that's approaching a real-world network. So again, we're going to start at the bottom. And the way this topology is architected is that we have a convolver pooling mini block, if you will. So, and then we stack those 3 times. And each time we do that, we are doing some subsampling or increasing the receptive field, and then we terminate with a fully connected layer, and this is a real common design pattern in these networks. So the way we would describe that is we have this convolver, 3x3 convolver, 3x3, S1 means stride 1, and 10 means the number of convolvers in the filter bank. And then as always, we take the output of this linear convolution layer and feed it through some nonlinearity. So it's the convolver plus ReLU, and then we do it again. And then we do some max pooling with a stride of 1, but we do a 3x3. So now we're getting some subsampling. And then we repeat it again, and then we repeat it again, and then we conclude with the fully connected layer, where each neuron is taking in all the input, and it's going to generate, in this case, an unnormalized probability measure that a given object belongs to a certain class. If we had that softmax layer, we might put that on the very top, and that simply is doing some mathematical exponential operations to the output of the fully connected layer. So now let's go over some of the popular topologies and networks that you're going to find referenced in a lot of the literature. So really, it all starts off with, in terms of convolutional neural networks, with this network called LINET in 1989. It was designed to classify handwritten digits, and my understanding is it might still be in use in some form or another by the post office. And it includes a lot of the common themes that you still find today. So you've got a couple convolution layers with some subsampling, again, which can be achieved, or which we would achieve with max pooling or with a stride of 2. So that happens a couple times. And then we have 2 fully connected layers. And then we conclude with a probability measure, which is this Gaussian, the Gaussian terminating layer. And a key point to note here is that as the receptive field is increasing, as the spatial dimension is being reduced, we're actually increasing the number of filters. The filter dimension gets much larger, and this is a common pattern that we find today in some of the more modern networks. Such as this guy, AlexNet. I'd be willing to bet that a lot of you have heard of AlexNet. This is the one that won that, this is the network that won the ILS VRC competition in 2012. The ILS VRC classification is a competition that's run against this ImageNet database, which consists of 1.2 million labeled images. And this is the network that really sparked all of this renewed interest in CNNs about 5 years ago. And it also includes a lot of these same design patterns that we went over today. So there's 6 convolution layers, followed by 3 fully connected layers, and typically we have a softmax layer that concludes that terminates the network. And this AlexNet is used for benchmarking purposes and is used as an illustrative example in all the literature. So it's good to be familiar with this one. Moving on, GoogleNet in 2014. Again, this one is a deep neural network. It improved upon AlexNet. And it actually, even though it's much deeper than AlexNet, it actually has fewer parameters. And one of the key facets of GoogleNet is this so-called inception layer. And what the inception layer is that you're running a few of these layers in parallel and then concatenating them. And then in 2015, this network, ResNet from Microsoft Asia, this is the one that has the sub 5% top 5 error. It's ultra deep, 152 layers, as opposed to the 9-layer thing from AlexNet. So, and one of the key points here is that because it's so deep, the authors actually introduced this thing called a residual mini block. And so the gist here is that the output of the ReLU-conv series is fed back into the input. And this was really done as an aid in training because it's so deep, it's so hard to train this. So they had to introduce this residual feedback in order to be able to train it in a reasonable amount of time. So in closing, DNNs and CNNs, they're really changing how we do computer vision. The fact that we do end-to-end learning means that we don't have to rely on handcrafted, frankly brittle features in order to do visual perception. DNNs have thoroughly surpassed hand-engineered features and traditional machine learning techniques. It gives us more capability to model these unconstrained, not as tightly controlled environments. And the really cool thing actually is that this toolkit, that these techniques actually apply to a bunch of other domains as well. For example, in audio processing, audio event detection, you can actually make an image out of your audio. You can take spectrograms of your audio input, treat that as an image, and feed it through convolutional neural networks and actually do audio event detection or isolated word recognition using these same techniques. It's pretty interesting. And lastly, for visual perception, the 3D convolutional layer, that's our featured building block. That's the guy that gives us the receptive fields and gives us our spatial coherence. So I hope you enjoyed this talk. If you want to learn more on the training of DNNs, which is a whole big topic in and of itself, you'll want to stick around until 12 p.m. For a shallow dive into training deep neural networks. And then at 2 p.m., there's going to be a tutorial on on a different application of these CNNs, object detection or localization. We talked about classification. This one will talk about localization. And then finally at 3:15, some new breakthroughs in unsupervised learning of DNNs. So we have some further resources if you're interested. And thank you for your time. And if you have any questions, now is your opportunity.
Thanks, Shehrzad. So, yeah, what we're going to do is if you have a question, raise your hand, and a representative in the back here will bring a microphone over so that you can actually ask your question.
So if you can give an insight into what are the typical insights that people have had in these, let's say, 4 years in building these networks based on the previously developed networks. That what I mean is if you had AlexNet and VGG was developed and so on, there was some intuition into, let's say, add a few more feature maps or bring a kernel size down and so on. So typically, what are these kinds of intuitions that guide researchers to finalize on a good network? Because all of these things will eventually also need training, and that takes weeks together and so many data samples and so on. So how do researchers make a transition from one established model into something else that really works?
Yeah, so, okay, my understanding is that really, okay, so one thing is this, the depth has gone up way higher, right? So simply, making it deeper and deeper and deeper seems to have, some build on the expressive power of these networks. Now so a lot of these kind of twists, these inception modules, these residual things, they're designed to aid in training, because the training of ResNet apparently took 8 weeks, right? So what you want to do is you want to build in little tricks that let you train these networks more effectively. Now, we didn't talk a lot about this. I mean, I think this will be discussed hopefully in some of the forthcoming talks, but there's this thing called transfer learning. So what it turns out is that actually, especially at the lowest levels, all the networks kind of converge to the same kind of pattern. And so you can actually take the third layer of AlexNet, for example, and you can transfer that over and retrain that, starting from that, and actually just maybe change the everything beyond that to get to fit to your problem. But in terms of what types of tricks, what type of funny tricks they're doing, I'm not quite sure. I don't know, Miran, would you happen to know? I mean.
Hello? Yes. So usually what people do nowadays, they start with one of the working ones, for example, VGG or even ResNet. And you have to basically train it for your application. You start big, but most of these networks are actually overspecified for smaller applications. Remember that ImageNet is actually a 1,000 category classification problem. Most of the practical applications, if it's sign detection, for example, traffic sign detection, you have maybe a dozen of traffic signs. So that's a huge simplification of your problem. So you start with one of the big ones, and you start removing layers and see which size fits you best. So there's a lot of that sort of tricks that people do, and you do get actually something smaller for your specific problem.
Thank you for a good talk, first of all. Secondly, I have a hardware background, and noticing that the number of layers are increasing based on the schemes, right? Just went from 8 to 20s to like 100 something. So how do you think it is impacting the hardware, and what will be the big challenges in hardware to resolve this in an embedded environment where power and area are especially important?
Yeah, that's a great question. So a couple things. So a lot of these networks, when they were first developed, they were developed in single precision floating point. So the first thing that happens is there's been a trend to using lower width data. So first of all, fixed point data. First, we went from 32-bit single precision down to 16-bit, and lately the whole push has been to 8-bit, and apparently, it's going to go even lower than that. So the first thing is a reduction in width of data types. Then there actually, in terms of the depth, at least on GPUs, that's what I'm most familiar with in terms of inference engines. You can actually stack up your input, and you can take advantage of a lot of these blast kernels like matrix multiply to kind of pipeline the data through. But in terms of VHDL optimizations, I'm probably not the right person to answer that. But I think fundamentally what you're going to be looking at is highly pipelined architectures and a reduction in bit width.
Hi, my name is Mira, and I'm from Cadence. I'm a writer, and I've only just been introduced to this since like January, so I'm really reading up like crazy. I read a lot of those things. My question is about stochastic learning. We didn't mention that, but as I understand it, that's when a system learns as it goes. And I'm wondering how that kind of fits into, you've got your learning phase, and you've got the phase where you then classify it, and those are two very specific and separate places.
Right.
So how do they fit together when, say, you're working in a car and you're wanting a car to learn, say, local driving styles or something like that?
Right.
So that's, what are the challenges with that, and how do they kind of fit together?
So okay, so so this talk was focused more on the latter, what you talked about, inference, the forward path. Okay, what you're talking about is actually training. Right? So that's a big topic in and of itself. So first of all, the whole thing about training a network is you need to have good data. Without good data, you're not going to get a good network. Garbage in, garbage out. Now, most people, for most applications, they're probably not going to have enough data. So there's a lot of techniques called data augmentation, which lets you augment your training data in order to get a network that works better. So for example, if you were in a car and you needed to recognize stop signs, you could, if all your stop signs were frontal facing, you might warp those images, okay, to generate more training data. You might flip them and do other things as well. You might sprinkle them with some sort of noise to augment them, and so that way you can kind of, I guess that's kind of stochastic. I mean, you would augment your data set to increase your training. I would encourage you to come to the next talk, which will probably go over that topic in more detail.
I'm Michael from Cadence. I have a question about the layered structure of these convolutions. So you described that the way most of these networks come out in terms of their functionality after training is that there's sort of a layer in the kind of like gradient functionality, like at the first layers, and then it gets into parts and then into objects and all that. So does that really happen no matter what, no matter how people train the network? And so to me, it is a little bit surprising that all these networks come out to have this kind of functionality.
Well, they're only going to come out like that if you have subsampling, right? If you don't have the subsampling, you're not going to be reducing the spatial dimension. You're not going to be increasing your receptive field. So there's nothing to stop you from removing those pooling layers or keeping the stride always at 1. So that's why. Now, it just so happens that for visual perception, because we need the spatial coherence, because we want to recognize that stop sign anywhere it happens to be in the frame, that's why we actually need that subsampling effect.
For instance, you could do a fully connected layer. Just everything's fully connected on an image, but then you're going to suffer from things like overfitting. So it only learns your data set, doesn't generalize.
Yeah.
So, I mean, all the subsampling and everything he's talking about really does help it generalize.
Right. You could, anything that you can do, you could do these with just fully connected layers, but it's going to be highly inefficient and probably very difficult to train. But in theory, you can do it.
Question. With the, when you have more than one object that you want to be classified, now would the weights and biases all have to be learned together, or is it separate runs of the engine, inference engine, or is it can be done with one run with a learned weight? How does that affect?
Okay, so the question is if you have more than one type of object that
To be classified.
that you want to be, yeah. So, so for example, this ILS VRC guy has 1,000 objects. ImageNet has 1,000 objects that you want to classify. So you just need to run it once, and what you'll get is you'll get a in your softmax probability, you'll get a probability that the horse is there and that the pedestrian or that the person is there. And everything else hopefully should be 0 or close to 0. So 1,000 outputs with yes, yes, your final output, your final softmax output in AlexNet, trained on ImageNet, is 1,000 numbers between 0 and 1. Yeah, and if you sum them up, it's going to add up to 1.
All right, last question. We have time for one more. Anybody?
Oh, we got one all the way back there.
Thank you for the great presentation. I had a question. So you're talking about that the probability all adds to 1. Is there a way, once you have trained it and you're in a production environment, you can get a confidence on its probability on each of those values? So you're classifying object into 10 items, and you said that the probability sums to 1. Is there a technique available where we can have a confidence on top of it saying that, hey, there's 60% probability that this is a cat. I can rely on it.
Yeah. You know?
You can have actually trained the network.
Yeah, you would need to have another class, a pseudo class that's like not. Like, okay, so if you have 1,000, let's say you have 1,000 objects, you need to have the null set or just something that's not in there, right? Like, I don't know, grass, or it could be anything that's not, that is definitely not part of your classification corpus. And then that, if the network is performing properly, it'll map to that one, to the not an object of interest category. I believe that's how you would solve this. So if you have a binary classifier, I think the way that usually works is you have present or not present. So it's not present is the present of it not being there. But I think if you have 3 or 4, more than 2, then you would have to have this null set.
All right, so let's wrap it up for now. Like I say, we're going to have the next session starts at 12, and it's going to go into more of the training, and et cetera. But let's just give another hand for Shehrzad.
Thank you.